In this video, I'm going to focus in on some key considerations we need to make when we're digitizing. What is digitizing? On the left, back when I first learned GIS, we learned all about the heads down technique, which is an archaic method which we see on the left. Essentially what you would do is you would trace a map or an image on a big board using what they call a puck, and then what you would do is you would mark the exact coordinates and you would put in nodes and vertices and edges and faces, and you'd create essentially a digital record by plucking away slowly but surely on this paper map. On the right, I was also part of the first group of GISers to learn how to digitize via computer. And so back when I was a GISer and an undergraduate student, my first internship was going through and digitizing the building footprints. So essentially what you're going to be doing on exercise 2, but I was doing it on desktop computer in which I was using underlying satellite imagery to see the houses. And they call this type of digitizing on a computer heads-up digitizing. A key consideration to make is when you're using an underlying base map to draw, let's say, county borders, it's going to be important that you have something that has a good amount of detail, something that is also designed for specific coordinates. For example, this map from the textbook on the top right shows different counties. Now, it would be nice to use this to find out population density, but it would be not nice, a very bad idea, to try to use these county borders to actually trace and create a new county-shaped file. So if I was wanting to create a county layer and I was wanting to digitize each of these individual lines and geographies, I'd want to get a very big file in which it's very detailed, in which I know there's not going to be any generalizations made regarding borders and boundaries. And so if I can zoom into something extremely close and it's extremely accurate, then I know my output's going to be much better when I'm doing the post-digitizing process. Further, if you're using analog data sources and hard copies, whether it be an old aerial photograph taken in the 1940s or a paper map published in a book, like the one you see here, often these sources will shrink, will swell, get wet, distort, be folded, creased, and in general become distorted. And so right here along the middle of this particular map, this Sanborn map, is a crease. And this was just a function of whoever was the one that scanned this particular image in. They didn't account for the fact there's this crease right in the middle of the particular map. Another example would be this kind of artifact left over that's maybe from a scanning process in which this particular polygon is not on the map, but it makes it appear like it is in this particular Sanborn map. In another one here, we see some color issues here in which it's kind of faded, in which everything looks kind of yellowish over here, and is different when you look on the other side of the map and things are a little bit more clear. There are a number of ways in a GIS for us to be able to detect if there are some digitizing errors, and some of them relate to our previously discussed term topology. And we're going to use the term node valency, and all that means is the number of arcs that connect to a node. These three are called a normal node, a dangled node, and a pseudo node. A normal node is one in which it has a valency of 3. And so what that means is it connects 3 or more arcs. And so here would be an example of a normal node. Notice we have 1, 2, 3 arcs that come to that one particular point. Another normal node would be located here. We got one there. Here we have 4 arcs, and then another 3 arc normal node there. A dangled node is one in which it has a valency of just 1. And so that's going to be one in which it's a single node at the end of the line. Whereas normal nodes, for the most part, don't indicate any bit of error. A dangling node, or dangle node, is one in which there could be a potential error, but not necessarily. For example, we might have a cul-de-sac or a dead-end court in which a dangling node would make a lot of sense. However, there are other instances in which a dangling node, which we see here, there, and up here, would be examples of digitizing errors. In this case, the node is extra. It's an overshoot. This line was supposed to stop at this particular node here. In this case, we see an undershoot, in which these nodes were supposed to connect to each other. Over here, we have an undershoot, in which this particular node does not make it to its destination, this particular line here. So whereas one went too far, the other one didn't go far enough. Finally, we have a pseudo node, which is one in which it has a valence of 2. So that's a line that's going to connect with itself or another line. Now, not always does this indicate errors, but it can be potentially redundant. The only pseudo node here we see is this one right there in the middle of this particular line segment. So note that it has one going in, one going out, so it's got a valency of 2. It might be added for a general purpose, like for example, this might be a street in which at this point the speed limit changes from, let's say, 25 to 55. And so that node in this particular case has a purpose. But if this line segment was all the same value and this node didn't have a purpose, we'd want to remove it. Something else to consider when doing some digitizing is to avoid the creation of what we call sliver polygons. And these often result from the incorrect practice of double digitizing, which is essentially the duplication or tracing of the same line twice. So let's say we have two polygons that were being drawn. Essentially what's happened is we've drawn the same line twice. We drew one over here, creating the red line, and then the blue line over here to create essentially new polygons that were created from the bad digitizing and the double digitizing of this one boundary. So the solution would be to, instead of drawing two boundaries, would be to append one with the other. If I was drawing the red polygon second, what I would do is I would append it and I would clip it and then draw the boundary on the outside, and then it would create naturally from there the boundary separating polygon red from polygon blue. And in ArcGIS they have various tools that will go in, find these sliver polygons and correct them. Often you see double digitizing associated with overlay or merging tools. And so here we have the overlay, in this case, of two different layers. The purple line and the purple color is census block groups. So it's a polygon geography. The mustardy color is our street center line. So the purple, the polygons, the block groups, were GIS data created by the United States Census Bureau, obviously a national organization. In the case of the mustard lines, those were created from digitizing done by people from the city of Indianapolis, and they're using extremely high-resolution photographs. Now, it's not an argument of which one's better than the other. It's, though, important to note that these lines don't match up. Why is that? Well, they are produced by two different entities with two different goals. Now, for the most part, the street center lines and the census block groups, these lines do match up, and that's a good thing. We want that to happen, especially in our urban areas and in our GIS layers. But we do see some offset here between the two layers. Oftentimes in a GIS analysis, it's not so much the spatial accuracy that's important, but it's the topological accuracy that's important. For example, let's say we're doing some geocoding. So we're using some, let's say, linear referencing. And so we're wanting to mark an address location on either the left side or the right. In this case, we're going to use the odd numbers. And so we're going to assume on the right side of this line, so essentially the south side of the line, are all the odd number addresses. Now, if I would be placing these dots along the south side of this mustardy color line, notice what block group they're located in. They're located in this block group, when technically all addresses south of this center line should be in this block group. So thus this would be an error. Addresses along the street center line that are on the south side of the street should be in this particular polygon, not this one. This means we've got some topological misalignment, and is often a situation that we come across when we are bringing in two different layers from two different sources created by two different humans.